Alright, so here is a simple sequential circuit and it's called a NAND latch. NAND because it uses NAND gates, and latch, we will see why it is called a latch. It's also called RS latch, and the meaning of this terminology will also become clear very soon. Alright, so here are two NAND gates, gate 1, gate 2. Two inputs, A going to the first gate, B going to the second gate. And the second input of the first gate is coming from the output of the second gate, like that. And the second input of the second gate is coming from the output of the first gate. So our inputs are A and B, and the outputs are X1 and X2. And now we want to prepare a table of the inputs and the outputs. Let us start with A equal to 1 and B equal to 0. So we have 1 here and 0 here. And we don't know what the other input of this gate is yet. But we do know that if this is 0, then X2 is going to be 1, because any one input of a NAND gate being 0 implies that the output must be 1. So we can say that X2 is 1. And now we come back to this gate. Its first input is 1 and this second input is also 1. And we know therefore that X1 must be the NAND of A and X2, and that is 1 and 1, and bar of that is of course 0, like that. So when we have A equal to 1 and B equal to 0, we have X1 equal to 0, X2 equal to 1. So that entry is now completed. Alright, next let us take A equal to 0 and B equal to 1. So this is 0 and this is 1, and by the same logic X1 would now be equal to 1 and X2 would be NAND of 1 and 1, that is 0. So that is the second entry. A equal to 0, B equal to 1, X1 is equal to 1 and X2 is equal to 0. Now let us consider A equal to B equal to 1. So 1 here, 1 here. And now X1 is A X2 bar, A X2, and of that, and then the not of that, so A X2 bar, that is X2 bar because A is 1. Similarly, X2 is B and X1 and not of that, so that is B X1 bar, and because B is equal to 1, it is equal to X1 bar. So what it implies is that X1 and X2 must be inverse of each other. X1 is X2 bar, X2 is X1 bar. And this relationship is indicated here by writing X2 bar here and X1 bar here. So X1 is the same as X2 bar, X2 is the same as X1 bar. Now whether X1 is 0 or 1, we don't know, and let us take two cases. For example, if X1 was 1 earlier and X2 was 0, then that situation will continue to hold because it does satisfy this relationship. Similarly, if X1 was 0 and X2 was 1 previously, then the circuit will continue to hold that state. So both of these are possible. We can have X1 equal to 1 and X2 equal to 0, or X1 equal to 0 and X2 equal to 1. And which one of these will actually happen depends on what was X1, what was X2 before. And in the table for the latch, we write this observation as previous. That means whatever was the previous condition, either this one or that one, will continue to hold. And that is why this circuit is called a latch, because in a sense the circuit has latched in the previous state. It is not changing. Alright, one last point. For a equal to b equal to 0, x1 and x2 are both 1. If we have 0 here, that means x1 is 1. If we have 0 here, that means x2 is 1, and that is irrespective of this other input. So for a equal to b equal to 0, x1 and x2 are both 1. But this combination of a and b is not allowed, and we will see the reason for that a little later. Alright, so we have written 1, 1 here, but we should bear in mind that this combination is not really allowed. Alright, now these names a, b, x1, x2 are not really used in practice. What we use in practice is some more meaningful names, and let us see what those are. And we start with some observations first. The combination a equal to 1, b equal to 0 serves to reset x1 equal to 0. And why are we saying that? Look at this table. A equal to 1, b equal to 0, x1 is 0. And this happens irrespective of the previous state of the latch. So if you go back one slide, you will realize that this is derived with no reference to the previous state of the latch. Alright. Similarly, the combination a equal to 0, b equal to 1, the second one, serves to set x1 to 1. We have x1 equal to 1 here, and that again is irrespective of the previous state of the latch. In other words, with a equal to 1, b equal to 0, the latch gets reset to 0. This entry here, a equal to 1, b equal to 0, the output of the latch, which we will consider as x1, is getting reset to 0. And with a equal to 0, b equal to 1, the latch gets set to 1. This entry here, a equal to 0, b equal to 1, and the latch output, which is x1, is now getting set to 1. So the a input therefore is called the reset or R input, because when this a is active or 1, then the latch is getting reset. The latch output is getting reset to 0. And b is called the set or S input of the latch. When b is 1 or active, the latch output is getting set to 1. The latch output x1 is denoted by q and x2 is denoted by q bar, and the reason for that is x2 is the inverse of x1 here as well as here. And if you recall, in the last slide we saw that in this third row, when a and b are both 1, x1 and x2 were inverse of each other. Only in the fourth row, x1 and x2 are not inverse of each other, but that row is anyway invalid. So this is our circuit diagram with the new input and output names. R here for reset, S here for set, Q, that is the latch output, and Q bar is the inverse of this. And here is the table that describes how this latch works. When R is 1, S is 0, Q is 0, and it is easy to remember this. R equal to 1 means something is getting reset, and that something is the latch output Q. So Q is becoming 0. S equal to 1 means something is getting set, and Q is getting set to 1 over here. When R and S are both 1, as we saw in the last slide, nothing really changes, and the previous state Q as well as Q bar continues to hold. And the last entry, as we have seen, is invalid, and later we will explain why this entry is considered invalid. Let us now look at some waveforms so as to understand this table better. Here is the R input for the latch. here is the S input, that is 0 and that is 1. Similarly 0 and 1 and so on. This axis of course is the time axis. Okay, now in the beginning up to T1, that is, we have R equal to 0, S equal to 1, and the output Q is therefore determined without any ambiguity. So R is 0, S is 1, so the flip-flop is set to 1. So we have Q equal to 1 and Q bar equal to 0. Alright, now at T1 there is a change. R changes from 0 to 1, S continues to be 1, and now let us look at this table and figure out what should happen. So we have R equal to 1, S equal to 1 here, and this says previous. That means Q will stay at its previous value, Q bar will also stay at its previous value, and that is what we see over here. Q remains equal to 1, Q bar remains equal to 0. At T2 there is a change. S changes from 1 to 0, R continues to be 1. So we have R equal to 1, S equal to 0. So let us look at this entry, R equal to 1, S equal to 0. So that resets the flip-flop. That means Q becomes equal to 0, and this happens irrespective of what happened in the past. So Q becomes equal to 0 and Q bar becomes equal to 1, and that continues up to T3 when there is one more change. That is, S goes back to 1, R continues to be 1, so we have R equal to 1, S equal to 1, and therefore Q and Q bar retain their previous values. So previously Q was 0, so it continues to be 0. Q bar was 1, it continues to be 1. All of these observations are listed here, and you can go through that once again if you like. The question we want to answer now is, why not allow R equal to S equal to 0? In this table, for R and S equal to 0, we say invalid here. So the question is, why is this invalid? Alright, so there are two parts to the answer. One, it makes Q and Q bar both equal to 1, as we have seen earlier. That is, Q and Q bar are not inverse of each other anymore, and it doesn't make sense to call this output Q and this Q bar. So that is one reason, but that is a relatively trivial reason. There is a much more important reason, and let us look at that now. Let us look at these waveforms which we saw in the previous slide, and if you recall, we had come up to here in the last slide. We had R equal to 1, S equal to 1, Q equal to 0 and Q bar equal to 1. And now imagine that R has gone to 0, S has also gone to 0. So we have R equal to 0, S equal to 0. Now when R becomes equal to 0, the output of this NAND gate becomes 1, no matter what the other input is. And similarly, the output of this NAND gate also becomes equal to 1 if S becomes equal to 0. So then we have Q equal to 1 and Q bar equal to 1. And that is what is shown over here. Q is equal to 1, Q bar is equal to 1. And that situation continues up to T5. And suppose that at T5, R has gone back to 1 and S has also gone back to 1. So now we have R equal to 1, S equal to 1. What does the table say for R equal to 1, S equal to 1? It says previous. Now the question is, which previous value? Is it Q equal to 1 or is it Q bar equal to 1? And there is a question mark here. What happens in real life is that depending on the delays of these two gates, the latch will finally settle down to either Q equal to 0 or Q equal to 1. That means Q equal to 0 and Q bar equal to 1, or Q equal to 1 and Q bar equal to 0. So there is some uncertainty about what will happen in this case, and that is why we consider this situation as invalid.